Okay, so photon enters the metal with enough energy, then the electron can be released from the surface of the metal. The minimum energy required is equal to Planck's constant multiplied by this value, threshold frequency. And every metal has a different threshold frequency and a different work function. When a photon is released, it is moving, therefore it has kinetic energy. If the photon that is coming into the metal has a greater energy than the work function, this extra energy appears as the kinetic energy of the ejected electron. And this is more coming to the final formula that you'll see in the formula sheet. The energy of the incident photon, HF, is equal to the work function, HF naught, plus the kinetic energy of the electron. So if you had the work function and the energy of the electron, you could work out what energy the photon arrived at. If you wanted to work out the kinetic energy of the electron as it leaves the metal, all you need to do is work out what did the photon arrive with and how much is left over. The value for what is left over is the kinetic energy. And just, if you want to, you can label this, you don't have to. Kinetic energy of the electron, work function, photon energy. If the frequency of the incident radiation increases, the maximum kinetic energy increases. Why do we think that that is true? Does that make sense? Does anybody want to explain why that makes sense? So frequency, what does that mean? How many occurrences per second? So the more photons of light that are hitting these electrons per second, the more energy they're going to have. Okay, so maybe we're thinking of it from this diagram as a case of one photon hits one electron. It's a beam, it's a constant bombardment of photons. The greater the bombardment, the greater the amount of photons per second, the more energy that this electron is going to gain, and then therefore its kinetic energy can increase. If we were to look at this graph, on the y-axis we have the maximum kinetic energy of the photoelectrons. So these are the electrons that are released from the metal. Down here we have the work function. Okay, the energy required to release electrons. All metals are found to give a straight line graph which does not pass through the origin. However, the gradients of each line is the same. Do you want to hazard a guess at what the gradient would be? Okay, the gradient is Planck's constant. You won't be asked to plot this graph. But if we were looking at metals 1 and 2, which one has the higher threshold frequency? The x-axis is threshold frequency, or is frequency. Here's F02, here's F01. Metal 2 requires a higher frequency, okay? Because it's further along increasing. All metals are found to give a straight line which does not pass the origin. However, the gradient is Planck's constant. That's what links this formula. The intercept of the energy axis is the work function. The value of Planck's constant, which will be given in the data table, is 6.63 times 10 to the negative 34. Now, if we think we've got no questions there, we can go on to an example. Just 1 second. If we just quickly imagine, a formula for a straight line is y equals mx plus c. On our y-axis, we've got ek. Our gradient is Planck's constant h. F is our frequency. Our work function, hf naught, is below the axis, so it's a negative. So that graph shows us the formula as well, okay? Ek equals hf minus hf naught. Our work functions are down here. This is where we get that from. Okay, our gradient is Planck's constant. I'll move that so it's in the booklet, if I can. So light with frequency 9 times 10 to the 14 hertz. Falls onto a metal plate. The work function is 6.5 times 10 to the minus 19 joules. Determine whether a photon will be able to be ejected, will be able to eject an electron from the surface. So we've got frequency, we've got work function. We can work out the energy of the photons that are incoming to the metal plate by doing E equals HF. The tricky thing with this topic is just getting your head around the terms, which term means what, and that's just through practice, unfortunately. I'm just going to use the full number because we're being asked to provide a yes or a no answer, not a numerical answer. So, is HF greater than or less than HF naught? Is the energy of the photon, and that's what this is, remember. Would you say, Ahmed? Okay, it's less than. Okay, and you can put the numbers if you want. 5.967 times 10 to the minus 19 is less than 6.5 times 10 to the minus 19. So photon energy is less than, we'll call it the work function. Does that make sense? The only tricky bit is getting these straight in your head. What is HF? HF is equal to the energy of the photon. What's HF naught? That's the energy required to get electrons off the metal surface. F is the frequency of the photon. F naught is the minimum frequency required for that metal. The good thing about these questions is they stay very similar. They're going to ask you to work out if HF or E or HF naught. So we'll go on to the next page, stopping voltage. So in this circuit, we have electrons. This is the positive terminal, and electrons are trying to get to there. That's the plate. Oh yeah. So initially with the voltage set at 0, if light falls on the photocathode, a small current is observed in the microammeter. This value of the current can be altered by altering the radiance of the light. That means the frequency, how much is onto the plate. This will alter the number of photons falling on the cathode and hence number of photoelectrons emitted. The photocurrent is directly proportional to the intensity of the incident light. Evidence that intensity is related to the number of photons arriving on the surface. So you can shine light on this plate and use an ammeter and measure a current. That current is generated by the movement of these electrons leaving the surface. If the anode is positive with respect to the zinc plate, photoelectrons are attracted towards it. If the polarity is reversed, photoelectrons are opposed. Notice that this diagram is opposing the flow of electrons. If the voltage supply is slowly turned up to oppose the photoelectron effect, there comes a point where the voltage is sufficient to stop all photoelectrons. The value of voltage that requires is called the stopping voltage. So what does this mean? If there's light hitting a plate and electrons are trying to be freed, and you put a voltage, you can prevent the electrons from moving because you're using a voltage to keep them where they are, ultimately. Yeah, the voltage is acting against it. Now we know from before that the energy of the photon is equal to the work function plus the kinetic energy of the electron if V naught is the voltage required to stop the most energetic electrons, then for these electrons we could say that the energy is equal to the charge times the voltage, which equals a half mv squared. Because what's our formula? W equals QV, E equals QV, which equals a half mv squared. So we'll just pause for a second to try and visualize this. So electrons are trying to leave the metal plate because of the incoming light, and they naturally would just do that. However, we put this in a circuit and applied a voltage in the opposite direction to push them and keep them where they should be kept. The energy we have to use to keep them there, W equals QV, or because this varies depending on frequency, the minimum energy required to keep them there is W equals QV naught, which is equal to a half mv squared. If they're leaving the plate with velocity, the energy you're needed to keep them on that and stop them doing that must be equal to at least their kinetic energy. Do we follow that a bit? You can combine these two equations. Because we know that EK equals a half mv squared, and we know that a half mv squared equals QV naught, we can therefore substitute that in to this. And we know then that if the photon energy increases, The stopping voltage, the voltage you have to apply to stop the electrons moving, must also increase to match it. I'm just repeating this every time I see it because it makes you connect HF to photon energy. This is work function, although it's quite difficult to write that small with this pen. The stopping voltage depends on the frequency of the radiation and is independent of the intensity. Okay, could be as bright as you like, it's to do with the frequency. The one last thing we want to add in is that this is also sometimes called the gain in potential energy. Let's do a better arrow. Yeah, QVO. So we will pause there. We will go back to page 1 of the question booklet and start on question 1. Make sure to give yourself a bit of, make it easier. Why not write the formula at the top of the page or write down what each term means at the top of the page? Then you don't have to keep going back and forward to the notes. You're given all the constants you need. So let's try and work through those for about 15 minutes.